Okay, thank you. Thanks for inviting me and for this opportunity to talk about graph capabilities in the Microsoft SQL family of products and services. So I'm a principal PM at Microsoft working on Azure SQL database. I wanted to quickly kind of go through some of the background motivations for what we have as a relatively modest set of capabilities for graph functionality within our products. And then I wanted to show you a couple of these specifics in terms of how things look in terms of syntax and capabilities and so on. So as many of you probably know, Microsoft SQL Server has been around for a while, and when we look at a lot of the customer scenarios that people use SQL for, increasingly we are seeing a lot of these scenarios where there is a need for network slash graph type functionality within the product itself. So very recently, for example, obviously contact tracing as an example, classically CRM, content management, energy, network analysis, and even things like classic, searching for personnel. These are some of the scenarios which kind of inspired us to look at what can we do in terms of enhancing the Transact SQL language and SQL Server and its related family of offerings to more efficiently support these kinds of customer scenarios. So very quick spiel on what we mean when we say Microsoft SQL. It's actually a broad spectrum of offerings. Both, if you look at it classically, most of us are used to SQL Server, which is what you would run on premises. But we actually have various flavors of essentially the same engine, which can go all the way from running on small edge-based devices to more of a hybrid kind of scenario, to running on containers, and all the way up to a cloud native database, which is Azure SQL database. All of these share essentially the same engine, which is the Microsoft SQL Server engine. The good thing is the graph extensions that we built run on all of these different flavors of MS SQL, if you may. Again, just a very quick thing in terms of what are the classical kind of impressions that people might have about Microsoft SQL is that it is traditionally viewed as a scale up solution, single node scale up solution. At least for a couple of those scenarios that I showed in the previous slide, and specifically for Azure SQL database, we actually enable scale out in various ways, both by adding replicas of the compute, which is where you typically run your queries, and also by scaling out the backing storage. So there's a lot of material which you can read if you're interested in how we've implemented this kind of a scale out story. So I will leave that paper for further reading. Now let's come to what I wanted to focus on, which is the capabilities that we have for graphs in this family of products. I'll talk a little bit about the what and how, and then happy to take questions at the end. So in SQL Server 2017 and around the same calendar year 2017 timeframe, we introduced a modest set of extensions to Transact SQL, which is our query language for the Microsoft SQL family. First, we added support for defining tables as graph tables. So we can create a table as a node to start with. And to do that, you use traditional T-SQL syntax, which is a create table statement. It should be very familiar to most of you. But one of the things, and I just realized a little typo, I'm just going to fix it on the fly as we go along. But one of the things we enabled is the capability to define the table as the node. All the other traditional artifacts like defining constraints on the columns within the table, indexes, data compression, specifiers for whether the column can be null and so on still remain the same. So I think this is a kind of an interesting design that we adopted, because what we found was customers who were motivated to use SQL for these scenarios which involved a graph were very heavily driven by the familiarity with the language footprint, and also they wanted to take advantage of existing features like some of these things like data compression, for example, constraints, and so on. So for SQL, for Microsoft SQL, if you may, the graph is the database. So you have a database, you have multiple tables in it. We view that entire database as a single graph. In order to uniquely identify these nodes, at least for the node itself or the node table itself, we internally use essentially an identity column behind the scenes, which the user will then see as a pseudo column, which is called $node ID. So you'll see this in effect in a few slides going forward. But behind the scenes, it is a traditional SQL table, but with this $node ID column exposed to kind of uniquely identify the graph node, if you may. So dealing with these tables is just like dealing with a regular SQL table. So you can insert values into the table, you can query it, as we'll see. But internally, as I mentioned previously in the slide, the node table has this auto-generated identifier column, which is viewable by the user as this $node ID column. The kind of GUID-like artifact on the top is a way for us to uniquely identify that column. So when the user looks at the table and they do a select star, they will see this kind of JSON representation of the node. You'll notice that in this case, this is actually based on the LDBC person table. So you'll kind of see that we've used the natural keys to kind of seed the graph keys. And we are allowed to do that by kind of using some extensions that I'll talk about in a minute. So internally, that's the distinguishing factor, the fact that you have a node ID column for these node tables. Bulk insert is also possible into the node table, and again, coming from the LDBC SNB benchmark point of view, this is quite important when you want to do a rapid ingest of the data. So as I spoke earlier, you can just do a normal insert. In SQL, we have an ability to do a select from a bulk row set, which is reading from, in this particular case, it's reading from cloud storage. But it could also read from a file on disk. With this construct, one of the things we also allow you to do is to shape the node ID that we talked about briefly earlier, wherein using this tsql extension, which is called node ID from parts, we are allowed to construct that internal representation of the node ID. This greatly simplifies management of let's say when you want to later insert edges, which I will come to next, you already know that the node ID, which is the internal graph ID that is used by SQL, has the same essentially natural key that comes from the data, which is in this case, the person ID. So bulk insert is very, very important for a lot of customers because they want to, initially start off with existing data, and we wanted to make sure we can enable quick ingest scenario. So that was node tables. Similar to node tables, we also allow you to create edge tables. Now, the interesting thing about edge tables in SQL is, as opposed to traditional SQL tables, we can have tables edge tables which are completely empty, in the sense they could just have no user attributes or no user properties, but just be defined as an edge. Behind the scenes, this is possible again because we have similar set of internal columns which are maintained. The key things that are important from an implementation perspective are the from and the to identifiers, which are again aliased to these pseudo columns called $from ID and $to ID. So when you create an edge, a row which is an edge in SQL in an edge table, you have to give it the from and the to IDs. Those from and to IDs could be from any other node in the graph. So this is quite useful because classically, if you are used to dealing with foreign keys in a relational database, what we allow you to do is not just a single table, but from any other node table, set up a edge to any other node in another node table as well. We can do this because, as you might kind of guess here, we store internally the object identifier and the internal graph identifier for both the from and the to ID columns. So this is quite useful because it allows you to operate at the entire scope of the graph, have a edge which basically runs from any node table to any other node table in the same graph. We can also set up constraints saying this table can only support edges going from table A to table B, or table A to table A, or a combination thereof. So you can have these edge constraints going as part of the edge table, which allows a lot of type safety, if you may, in terms of using these edge tables correctly. And again, these edge tables function as any other table in MS SQL would. So you can define indexes supporting graph traversals, for example, from forward traversals, we'd have an index on the from to, and if you're going backwards, which is right to left, if you may, in a expression, we have an index if you want, you know, on the to from pair, and so on. You can also have attributes, as I mentioned, but those are completely optional. So if you look at a graph edge table in SQL, this is how it looks. And you can see these from and to ID columns also contain the source table, which is the name of the table that they come from, and the graph ID that they are essentially referencing. These JSON representations are computed. They are not stored in the database as is. In the database, it's just integers. When you view it using a select statement, you see this kind of more readable JSON. Each edge also has a unique edge ID, but it's very rare that we typically have to deal with that. But it's used to mainly enforce, let's say, a duplicate edge. You do not want to have a duplicate edge. You can use that to kind of constrain and enforce uniqueness. Inserting into edge tables, there's two ways. You can either do the, if you're just inserting one row at a time, you can select the corresponding node ID from the node tables that they come from. And here, of course, this edge is just talking about knows. So like person knows person. These node IDs could come from different node tables, as I already mentioned. So this is one way to do it. Another way to do it is if you already knew that the node IDs in the node tables are composed from the underlying natural key, like in this case, person ID, you can again use the same extension that we talked about earlier, which is node ID from parts, and that allows you to save some, kind of operations in terms of having to query the underlying table just to get the node ID. So this, if you go further, you can combine that with the bulk mechanism that we talked about earlier. So bulk insert into edge tables is supported as well. And again, you'll notice the use of the node ID from parts to kind of prefabricate the correct kind of structures that are needed for quickly populating these edge tables. In kind of summary so far, what I wanted to emphasize is node and edge tables present a very familiar interface to experienced SQL users. From the Microsoft SQL family of things, at least most of the syntax that they used to just works. Data types, constraints, indexes, data compression options, security mechanisms, etc., all just work. So so far, the key message I want to kind of say is that one of the reasons why we shaped this the way it is today and why customers use it is familiarity and the fact that they want to use a lot of the other surrounding features and functionality that Microsoft SQL family of products already provides. Um, so once you have these node and edge tables, we provide extensions to Transact SQL, which allow you to do pattern matching. So to start with, we provide a match operator, which is quite similar to other implementations that we have already looked at. Like you see somewhat similar ASCII art type syntax. One difference is the edge. As it stands here, this is an edge table. We do not support wildcards. So for example, you can put a star there and say traverse the graph through any type of edge. There are other ways to implement that pattern, as I will come to in a few slides, but the syntax here will be predominantly a defined edge table. You can combine and make more complicated expressions, just like you would expect to see in typical pattern matching expressions. I've just kept this simple for now. So just as an example, if you wanted to implement the LDBC SNB IC2 query, this is how it would look with the match operator. So you essentially toss in the tables that are the graph tables along with any other non-graph tables that you want to combine. In this case, we are looking for pretty much messages created by a person, that you know, and in this case, this is how we would kind of construct IC2. So for users of Microsoft SQL, this is an incremental and familiar way to get to the best of pattern matching with a like a ASCII art type syntax combined with what you have with traditional T-SQL. You can do a lot more complicated things, obviously, with so here's IC1, which is interactive complex query 1 in LDBC SNB, and that looks at friends of friends, and then friends of friends of friends. So a naive way to implement that query to start with, and is, and it's not a bad way, it's quite performant, is that you could just write a series of match expressions which have increasing level of traversal through the graph. So here you'll see you're kind of looking at like a more complicated expression, which is a compound predicate saying, hey, we are traversing through this graph 2 hops, 3 hops. You wrap all of that up into a CTE, which is a convenient way of saying, hey, this is the part that identifies the friends that I am looking at. And then you can reference that CTE in an outer query, which, for example, in this case, is retrieving more properties associated with those friends in your network. So you're looking at emails and so on. So this is IC1, fairly a long way of doing it, but fairly performant and easy to read once you get kind of used to the syntax. In SQL 2019, and around the calendar year 2019 timeframe, we introduced an additional way to do more recursive pathfinding type queries. So match was extended to include shortest path, which allows you to specify a pattern inside the recursive section of the pattern, which is identified by this parenthesis here. You can optionally specify length or just put a plus there, signifying that you want to look for paths of any length. This recursive path, because it's a path, we had to extend T-SQL in a couple of ways to recognize that certain table references are for path. So knows, and the second person that you're, which is the eventual target that you're going to reach through this traversal is referenced using for path. And because these for paths are paths, we had to add again extensions to Transact SQL to be allowed to allow aggregations. Aggregations are of various forms. One is the simplest thing, and typically the most useful one is you can just take the last value from the path, which is typically what you want, which is the end result of that traversal. You can do counts, you can do sum, you can do string ag, and so on. So there are a limited number of aggregations which are supported over the path traversal. In this case, again, this is IC1 from the LDBC SNB. So all that we are looking at is typically the last person that we reached through this traversal, and we're looking at 1 to 3 hops. You'll notice here the query is a little more concise than the previous one. Obviously, with the recursive query, it does have its implementation overhead. So like the SQL engine has to do a little bit more work to support the generic walk through the graph, if you may. So performance of these two queries will look different. In general, the match, the brute force or the naive set of match expressions that we saw earlier will typically be a little faster than this, but this does lend itself to a lot more readable kind of usage. So yeah, so this is the set of extensions that we added to support both pattern matching and more of a pathfinding kind of a functionality. We currently are limited to returning only one shortest path. So for example, if you wanted to get all shortest paths between nodes, we do not have that natively. There are of course ways to work around by using your own implementation of like breadth first search over the graph and so on. So this is kind of like the query aspect. You can keep extending this to more complicated scenarios. There are a lot more things you can do with the shortest path. So for example, a lot of our customers, so SQL always had support for hierarchies in the form of recursive CTEs, and later we introduced a native data type as well, which is called hierarchy ID. Some customers found that they wanted to work with hierarchies through SQL Graph, and SQL Graph makes it relatively easy, again using the shortest path along with match to walk hierarchies efficiently. So we see this kind of a pattern quite frequently being used by a lot of our customers where they want to use traditional T-SQL and not have to deal with complicated syntax, writing recursive CTs and so on. So these are some examples from the shortest path point of view. Moving on quickly to what else can we do with this set of functionality that's supported. Recall in one of the earlier slides, I said match doesn't support a wildcard, and that holds true. But one of the things we can do is support things like derived tables, which is typically used for filtering out sets of nodes or edges or both, which you do not want to include in a particular query. But from the viewpoint of the wildcard specifically, one of the interesting use cases is if you define a union view on top of graph tables. In this case, for example, again, from the LDBC SNB schema, we are using abstraction on top of the post and the comment tables, which we call a message, and message is just a view in this case. This view can then be referenced in traditional match expressions, including shortest path queries as well. So this is kind of useful because when you have lots of very similar but still different tables which you want to then use in a single query, constructing a view with a union all on top of all your graph tables is one way to accomplish the wildcard kind of functionality that we talked about. There's variants around this. Again, I don't want to get too detailed here, but many times we come across questions from customers where they want to store very different sets of properties for different nodes. The way that we could do that is obviously have different tables, each being a node or an edge table, but SQL supports JSON data, parsing and working with JSON data as well. So one of the approaches that we tell them is you could actually have a generic property bag, which is represented in a single field in a node or an edge table, and then use JSON primitives within SQL to work through that. To kind of close out, one last thing, and this is specific to SQL Server in its classic sense, where you can, you do not have a security kind of a concern around running external scripts, for example. So SQL, starting from SQL Server 2016 onwards, allows you to execute external scripts. We initially allowed you to execute R scripts, and then we extended that to Python, and now I believe even Java scripts as well, Java programs as well. So there are some interesting things that open up with this. Given SQL is predominantly, at least the SQL graph extensions are predominantly aimed at more of the interactive operational query footprint. There are some customer cases where they wanted to run more analytical algorithms on top of this graph data without taking it out of SQL into a third-party system. So one of the things we can do with SQL Server, at least, or with Azure SQL, we have this thing called managed instance, which is kind of like a stepping stone to the cloud versions of SQL. We can execute external scripts, which in turn connect back to the SQL instance on that same machine. And they quickly can pull the node and edge data, and then you can use traditional libraries like NetworkX, for example, in this case, to do whatever it is that you want to do. In this case, this one, computes centrality and then runs an algorithm to see, how many connected components are there in the graph and so on. And then that data can be returned back to SQL fairly seamlessly in the form of a data set. In this case, I've just printed some output from the script here, just to kind of show you behind the scenes what's happening. But this kind of a handoff between traditional T-SQL and these extensibility mechanisms via Python or R scripts is quite powerful, because then you can do some analytics kind of stuff with these scripts, push the data back into SQL, or present the results to users and so on. So I just wanted to kind of give you that breadth view on these capabilities. I think, I don't know, in terms of time, if there's more questions, I can take those. But there's a lot of links. I'll be sharing the deck with Gabor, and he can post it up on the site. But hopefully that gives you a gist of what we support with Graph. It's a modest set of extensions, but it does enable a whole bunch of use cases for a lot of our customers. So hopefully you found that useful to learn about.
Okay, thanks very much, Arvind.
Okay.
We have a question in person from Alistair, and then we'll follow with Oscar's question.
Oscar was first, actually.
Okay, so Oscar, please unmute and go ahead.
Okay. Hi, Arvind. This is Oscar van der Les from Oracle. Thank you for your presentation. So conceptually, your data model is very similar to SQL PTQ. That's your store your, basically you have tables that are either vertex or edge tables or nodes and edge tables. Mm-hmm. So I was wondering if there's any interest in Microsoft to adopt the create property graph statement that's being standardized, and I guess similar for the syntax of the pattern matching. Mm-hmm. I know there was some interest in the beginning when we started standardizing, but maybe, yeah, if there's interest in like adopting what the pattern matching from GQL and SQL PGQ.
Yeah, this is an open area of discussion even internally. I think there's a lot of interest in looking at all these evolving standards, especially GQL as well. And one of the and again, I don't want to make forward-looking statements on this call, but one of the approaches we've been taking with a couple of these scenarios is like we may start offering gateways of some sort, like maybe a layer in between which transpiles or converts and whatever syntax it is that the user wants to see, whether it is GQL or other flavors or OpenCipher and so on, back to SQL native graph queries. So obviously this is a forward-looking statement, and I don't want to commit anything. But yes, we are closely monitoring the broader community, and then we'll have to decide based on funding and prioritization on our end how things go. But yes, I keenly am following, and I really found the sessions today quite interesting as well on the standards being discussed.
Okay, thanks. Alistair has another question.
Yeah, related question. It's a while since I checked in on this, but at one point there was a lot of interest in the Cosmos DB community in getting Cypher support at the time, because GQL wasn't really on the table. They supported interface as well as the Gremlin interface that was originally introduced. And this kind of, I mean, obviously, as Oscar was pointing out, a very close parallel with the, you know, the pattern matching and so on and so forth that, you know, that you've implemented in the MS SQL environment. Do you know whether there's plans there? I mean, obviously, if it's not something you can discuss, you know, understood, but I'm sort of interested in whether you want to, as a company, kind of get more and more sort of a single story, if you like, in terms of that, you know, these kinds of interfaces. Yeah.
Yes, yeah, and it's a little, I would hazard making too many specific statements, but yes. Also keep in mind, LinkedIn is a Microsoft entity in a broader sense, so Liquid and other things, there's broader conversations between all the teams at large. Yes.
Thanks.
Yeah.
One more question for Leonid. Please come here.
I was just looking at the code as you were showing it, and I noticed that you have paths annotated with plus, which presumably means one or more edges. Do those paths always have to be preceded by shortest, or is that a language requirement or not?
Yes, when we'll have to use shortest path if we need to, you know, have a path being you know, queried. With match, you have to explicitly then put in all the tables that you would like to. So you saw the brute force approach that I initially presented, and yeah, so the shortest path is a semantic and syntactical thing that we need to.
So but that's the default semantic, right? So you're not allowed to have plus without shortest.
No, not yet. not at this point in time. It's part of the syntax. Yeah, and a lot of it, a lot of the quirks and specific implementation that you see today is perhaps also an artifact of we have to work in the broader, within the constraints of the broader T-SQL grammar, so the parser and so on and so forth. That's why, for example, we couldn't use square brackets because square brackets in T-SQL have a different connotation. That's why we use the round, you know, brackets and so on. So there's lots of those, I think, within the constraints of the broader MS SQL heritage and you know, legacy. So some of these quirks are partially because of that.
All right, thanks.
Okay, thanks very much again.
Hey, thank you for the opportunity. Yeah.